So now I'm going to talk about how to construct the confidence interval with pivotal quantity. First, find A and B such that the probability that Q is between A and B is 1 minus alpha. So Q, distribution of Q does not depend on theta. So usually we can easily find distribution of Q and also find A and B. And then define Cx would be the interval based on Q, where Q is greater or equal to A and less than or equal to B. We can define confidence interval. Then, okay, let me back up. So we first construct the confidence set, not the interval, confidence set with the pivotal quantity. So we find A and B such that the probability that Q is between A and B is 1 minus alpha. So we find such A and B and we construct the confidence set based on A and B. Then if Qx is monotone in theta for each x, then this confidence set is interval. If Qx is increasing theta, then confidence interval is we can find lower bound and upper bound. So lower bound is the function of A and X, and the upper bound is function of X and B. If Q theta, X theta is increasing theta. if qx theta is decreasing theta, then the confidence interval is this confidence interval is the lower bound is based on the b, and the upper bound is based on a. So here, when we find confidence set based on the function q, and then when you find the expression in theta, if qx is increasing theta, then lower bound, because it is the increasing in theta, so it is the monotone. So a is the component to be in the lower bound, and the b is the component to be in the upper bound. If qx is decreasing theta, then this due to this monotonicity of q theta, and now it is decreasing in theta, so now this interval is the reversed. So b is the function in the lower bound, and the a is the component in the upper bound. So let me give an example. Let x1 to xn be IID in exponential lambda. We will construct 1 minus alpha confidence interval. And we showed that let t equal to sum of an xi, and showed before that 2 times sum of xi divided by lambda, so t divided by lambda, 2t divided by lambda is a pivotal quantity. So we showed that just before. And then if t, the t is a gamma expression with parameter n and lambda, because it's sum of xi. And then 2t divided by lambda is gamma times n times 1, which is equal to chi-square distributed with 2n degrees of freedom. remember that the gamma distribution, the chi-square distribution is the special case of the gamma distribution. And this gamma distribution is so gamma and n1 is the chi-square distribution with the 2n degrees of freedom. Then the interval that we have based on this chi-square distribution is, so we first need to find upper bound and lower bound. We first need to find a and b. So 2t divided by lambda between a and b, the probability is equal to 1 minus alpha. And then here, a, you can take chi-square with 2n degrees of freedom 1 minus alpha 1. B is chi-square distribution with 2n alpha 2, where alpha 1 plus alpha 2 equal to alpha. So we are gonna have this is the chi-square 2n distribution. We take a is equal to be x2n alpha 1. This is alpha 1. B to be alpha 2, where this middle part is 1 minus alpha. So we can choose a probability in each tail. And then we pick up so that we define alpha 1 and alpha 2, which is sum of this alpha 1 and alpha 2 equals alpha. So we find the values in the chi-square, the percentile value. So for the lower end, we find the value that chi-square distribution 2n and then with a percentile 1 minus alpha 1. And for B is percentile the alpha 2. Where alpha 1 plus alpha 2 equal to alpha. So one minus alpha constant interval is by inverting these quantities. We can get the lambda is greater or equal to 2t divided by p, and lambda is less than or equal to 2t divided by a. That's the 1 minus alpha constant interval. Then especially you can take alpha 1, alpha 2 the same, which is the alpha divided by 2. So you can see that here the 2t divided by lambda is the decreasing in theta. Then you can see that this b is the component in the lower bound in the lambda in terms of lambda, and a is the component in the upper bound. So let me give another example. Second example is we have mu. Normal distribution mu sigma mu and sigma square mu. So they're both unknown. So we have the normal mu sigma square and then mu and sigma square are both unknown. And we will construct 1 minus alpha constant interval for mu. So here, t minus 1 is x bar minus mu divided by s by the square root of n. This t n minus 1 follows t distribution with n minus 1 degrees of freedom. If we were to find A and B such that probability that A and B, T n minus A and B is 1 minus alpha. So same as before, if we have T distribution with n minus 1 degrees of freedom, so we find A and B such that A is the 100 times 1 minus alpha 2 percentile of the T distribution under n minus 1 degrees of freedom, and B is the 100 times alpha 1 percentile of the T distribution under n minus 1 degrees of freedom. So that this lower, the tail probability is alpha 2 and upper tail probability is alpha 1, so that the middle probability is the 1 minus alpha, which is the confidence coefficient. So we take A So we take the alpha A equal to T n minus 1 and 1 minus alpha 2, and B is a T n minus 1 and alpha 1, such that alpha 1 plus alpha 2 equal to alpha. The constant interval is like this. Then the famous confidence interval that we can get is if we take alpha 1 alpha 2 is to be equal, then we can get the same as the we can get the famous 1 minus alpha confidence interval, the two-sided, for mu, so which is the confidence interval for one sample case. So next example, still we have a normal sample, normal random sample, and mu and sigma square both unknown, and find. Now we were to find interval for sigma square. Not sigma square, sigma. So in this case, we like to use this fact, n minus 1 times s squared divided by sigma squared follows a chi-square distribution with n minus 1 degrees of freedom. This implies probability that the s minus 1 times s squared divided by sigma squared is greater or equal to a and less than or equal to b is the 1 minus alpha. Then we can use this is the fact that the pivotal quantity is chi-square distribution with n minus 1, which does not depend on the sigma. So you can get that. Just take a b, chi-square distribution n minus 1 alpha 1. And we take a chi-square distribution n minus 1, 1 minus alpha over 2, such that alpha 1 plus alpha 2 equal to alpha. So, which means that your distribution, chi-square distribution, n minus 1, your point to the n chi-square n minus 1, 1 minus alpha 2, and this point, this is a, b is chi-square distribution n minus 1 alpha 1, where lower tail probability is the alpha 2, upper tail probability is alpha 1, middle is 1 minus alpha. So B, and then in terms of sigma, we have the n minus s squared divided by b square root of that is the lower bound of the sigma, and n minus 1 times s squared divided by a, take a square root in it, is the is upper bound for the sigma. So we can get the 1 minus alpha constant interval for the sigma. And then you can take alpha 1, alpha 2 equal to same, alpha 2, so that you can allow the two tails have the same probability and then get the confidence interval.